Thank you. Okay, good to see everybody. We're quite honored today to have Professor Dirk England from MIT here to come talk to us as part of our Quantum at Harvard seminar series this year. Professor England is actually unusual in among the list of speakers because almost all of our speakers have either talked about materials or specifically about devices, right? Right. Professor England is going to be the first person to talk about systems and about systems integration. And his group actually does both. They do device work, but they've also have focused a lot of attention on developing next generation systems to kind of make this quantum internet thing, whatever we think it's going to be, possibly happen. And so I'll get out of the way and let Professor England go ahead and talk about the work in their group.
Thank you so much, Bill. Hey, everybody. Great to be here. Thanks so much for the introduction and for the invitation. I will talk about systems, and I will actually focus mostly on systems because much of the devices that we pursue, you've already seen some of those in the recent speakers seminar series. I know that, for example, you've heard about color centers and diamond and so forth. I'll touch on that only briefly, although it does make up a large part of our group's effort. But I thought I would take the opportunity to tell you specifically, as Bill said, about systems. And here's one. This here is a photonic integrated circuit that comprises about 500 or so individually controllable components, controllable in phases that are applied to waveguides that you can just barely make out here. These horizontal lines here are waveguides in silicon surrounded by silicon dioxide, and we apply phase shifts with electro-optic modulators to these waveguides to make, in this case, a system on chip for various applications. This is one of the examples that I'll talk to you about that we have found to have broad applications in quantum control, but also in machine learning AI. And I'd like to just give you some sense of the application areas and sort of how we've progressed in that field. Let me begin with actually the original motivation for developing these kinds of systems. What you see here is an array of ultra-cold atoms. These are rubidium atoms cooled by laser cooling methods to temperatures around 1 microkelvin. Now, many of you will have seen a photo like this. This is an actual photograph. This is work pioneered by the groups of Mikhail Lukin, Markus Greiner, and other members of the Center for Ultra-Cold Atoms, MIT and Harvard, in particular also Vladan Vuletic, my colleague at MIT. And so these are in fact one and only one atom, once at a time. And I'd like to remind my friends at IBM and Google who work on superconducting quantum computers that by the standards of microkelvin temperatures, their lowest temperature dilution refrigerators are hot. They're 10,000 times warmer than the temperature of these atoms that sit in close proximity, just a few centimeters away from a room temperature apparatus. So that's thanks to the power of laser cooling. Now, it's become possible in recent 5 years or so to array atoms neatly into these kinds of registers where they can be used for storing quantum information. For example, in the internal electronic or nuclear structure of these atoms, you can store quantum bits or qubits and interact these qubits via, in this case, Rydberg gates. So basically you push the electrons to an outer orbital to kind of poof up the atom so that the electron is almost ionized, and that allows some strong dipole-dipole interaction to take place over some range of some microns. And that allows you to create a full gate set for quantum computing. You have local gates using the defined structure of these atoms, and you have entangling gates using this long-range Rydberg interaction. But the way to apply the gates requires precise laser fields. Okay, so for example, for individual qubit manipulation here, you have to apply a particular sequence of optical fields And that has to be done very precisely, and you have to do it at scale. And this is where no technology exists to solve that problem at scale. Whereas you can have modulators in the right wavelength range, 780 nanometers or so, that perform the necessary operations on single or perhaps a few qubits of this type. It's impossible at the moment to scale to thousands or indeed millions of qubits that are deemed necessary to realize, as far as we know, a practical quantum utility. Okay, so there's a gap here in the technology. We know how to control a few qubits or a few channels, many qubits with few channels of control, but what we want to do is do this at scale, thousands of channels simultaneously, or really millions of channels. So this is where these kinds of photonic integrated circuits can solve an important problem. So I'll tell you a little bit about the kind of circuits we're making for this problem. And that, it turns out, is very similar to the kind of circuit that we're making for qubits that we operate in our own laboratories at MIT. Actually, I don't work in my laboratory on ultra-cold atoms. I work with collaborators. These are fantastic people to work with. So what I do in my lab is an analog to that. These are made of color centers in materials, atom-like qubits or quantum emitters inside of materials like diamond that many of you are well familiar with. So I don't really have to repeat that too much. Nitrogen vacancy center, silicon vacancy center, tin is our favorite at the moment. Okay, there's a hit list, I think. But I will tell you about a recently discovered color center that is it's a group of color centers in silicon. And these are native to silicon, and their properties are similar to color centers in diamond, but now being in silicon, you can take advantage of the manufacturing base and the semiconductor control that's possible thanks to the kind of manufacturing that made this possible and what makes our cell phones possible and all of this. So I'll tell you a little bit towards the end about quantum control at scale for these types of qubits. So along the way, and my group has been pursuing this, since we started, 13 years ago or so. We were motivated really by the atom control problem. But along the way, there's this thing that happened called AI. I'm sure you've heard about it. Really starting in 2012 is really when the second, version 2 of AI started to take off. And we realized some years later that the systems that we were building for this atom control, namely precise analog optical control systems, were also interesting to solve problems in machine learning hardware. And so that's the other part of the talk. In fact, the talk that I want to focus on here, because I think that is less familiar to folks here. But there's interesting connections. I don't know exactly where it goes, but there are really deep connections between quantum computing and networking and machine learning. It's really how nature computes. And I think it's a fun time to work in these fields because we are really amidst a renaissance in computing where the standard paradigm of Moore's law scaling, Delaunay scaling, is giving way to a search for new ways to use nature to compute. And what does computing mean anyways? It's to perform maps, right? To transform information from one basis to another. And so I'd say quantum computers are part of that renaissance of in-physics computing about these claims of quantum computational advantage. This is for certain esoteric math problems so far as we know. We don't yet know of a single example of a quantum computer having true practical utility. But on the other hand, we don't know that there doesn't exist a noisy intermediate scale quantum computer that can give practical advantage. There's a discovery really going on. It's an exciting time. We do know, however, that in the long run, when you get to scale, that if you can error-corrected quantum computing, we do know of certain specific examples where you do have a computational advantage. And so that drives a lot of our work also, is how do we get not to doubling the number of qubits, but how do we get to a system that can scale to the realm where we know that quantum advantage exists. And that, as far as we know, is when you have some thousands of logical qubits, which with present sort of estimates on overhead for error correction means some hundreds of thousands or perhaps millions of physical qubits to start. Of course, then you want to scale. So we're interested in building platforms that can really reach scale for utility. Okay, but in the picture of this renaissance of computing, you have also simulators. But I think in particular, and this again is what I'd like to focus on here, is you have a lot of really exciting opportunities in rethinking how we compute in the first place, in particular in the context of machine learning and AI. By the way, protein folding was once thought to be sort of a major reason to pursue quantum computers. Now, DeepMind has made that actually solved, essentially has solved protein folding in many respects using AI methods. So just to give you a sense of the application areas that optical control systems can address or needed for, here I've given I show you a spectrum of, in particular now focusing on quantum computers, different types of quantum computing architectures that have different types of demands on the optical control systems. On the left lower hand side, you have the type of cold atom arrays that we looked at a moment ago, or similarly, perhaps trapped ions, where the optics is necessary to control stationary physical qubits encoded in some fermionic system. But the optics itself doesn't hold quantum information. So it's still a hard problem, but it's not as demanding as some other problems that maybe we have to solve as we go towards the right-hand side here. So in particular here, let's say, what if we wanted to connect quantum computers, perhaps of this type or using color centers or so, then you have to use optics not only to control qubits, but also to move quantum information, right? In the, for example, encoding of weakly excited optical fields like single photon excitations of optical modes. So here you need to not only do this optical control, but you also need to be able to pass quantum information encoded in flying qubits, and with reasonably good efficiency. So there's a lot of work also, of course, going in this area at Harvard on, let's say, Marco Loncar's group in quantum state transduction and so forth. We would like to also be able to not only move quantum information with optical qubits, but also interact optical qubits. And that is, and there are sort of two ways to do that. Number one, to use intermediate interactions to mediate interactions with matter between optical qubits, with matter in this case consisting of many atoms, like in a nonlinear crystal. And so these, I would say, are matter-assisted entangling gates or matter-assisted two-photon gates. This is an example where you have a control and a signal photon, where the control can apply a CNOT gate on the signal photon on the signal qubit using some nonlinear optical interaction. So my group does a lot of work in trying to figure out how that can be done at scale and with sufficient. And the other way to do all optical quantum computing puts the interaction, the linear, actually into the process of measurement. And so these are measurement-based quantum computers or linear optics quantum computing that are pursued by some large companies you probably have heard of, like PsiQuantum or Xanadu, are pursuing basically some range of these methods to do quantum computing. Now, all of these things are hard, and they require really new ideas and new control systems, in particular in optics. So I consider sort of over time, although I'm trained as a physicist, I've become more and more interested in the engineering, which in and of itself, control theory and the application in building large-scale electro-optic control systems, because that's ultimately what I think what we're really doing. And so that requires you to develop, and that's present because you're so tied to the physical hardware, you can't really take like one thing in isolation. You can't work at an abstraction layer the way that you build software on classical devices. You really have to think about the co-design of algorithms, the photonic control, and the circuits and electronic control. And so you'll see some of that work as I go forward. But now I want to just shift gears. So now this is sort of like, this is about roughly half of the activity in my group up to here. But I want to focus in particular and like apply these methods that we were just talking about to the AI problem. Okay, so really the second path of the Renaissance, or the second maybe viewpoint in the Renaissance in physics of computing. So here, just to get us all on the same page, let's just briefly review what really is at the core of this revolution in machine learning over the last roughly decade or so. It started with the discovery that if you took some idea that had already been around for decades prior, neural networks, but if you made them deep, which means that you have many layers in between the input and the output, that deep neural networks were much more powerful. So there's an emergence of the compute capacity which once you get to sufficiently large scale. So DNN in its simplest form is shown here. You have some input layer. You could think of this as an image or so on which you would like to perform some image recognition. And that's encoded in a vector. So you like take your image and you have to vectorize it into a long vector. Let's call that input vector X. And you'd like to tell, is there like a cat or a dog in that image? And that is the desired output map. So how do you go from the input to the output? Well, so you can layers that have some repeated features. They have synapses that take in the input with some weight, okay, from the prior layer. So for example, this neuron here would take the input from all previous layer neurons, but not equally, it weights the inputs, okay? And so that means that these weights here can be represented by a matrix, because in this case, for example, you'd need three weights for weighting each of the prior neurons, and then you do that 4 times. So you need a total of 4 times 3 or 12 values to store the weights, essentially the thickness of these lines. So these are the model parameters of the neural network. And then you linear function, like a ReLU is a popular one, on down the chain. So by this kind of architecture, AlexNet and these recent like major advances in AI have become possible. This is one architecture. There's actually other types of architectures that are shown here. There's a nice summary of the zoo of machine learning methods from the Asimov Institute here. But they share something in common, which is that if you want to implement them on a conventional computer, you spend a lot of time on linear algebra. Why? Because the biggest difficulty hurdle here is at every layer to compute this linear algebra transformation from one layer to the next. This can require a lot of linear algebra compute. And it's really one of the central bottlenecks in inference and also in training. How do you find the weights in the first place? And so this is where new forms of computing are being explored to see if one could simplify those that hardware, that compute bottleneck. And this is becoming an increasingly pressing problem. You can see this from this chart here. Plotted here is the number of model parameters for leading ML systems. Of course, we start here in 2012 or so with AlexNet from the University of Toronto that famously won this, like, just beat every other method for image recognition. Now that thing had some tens of millions of model parameters. Then people learned how to sort of compress these methods, but there has been a steady trend to exponentially large scaling of leading neural. So line, and this is already rather outdated from a previous paper that we assembled these things. But in this trend line, you see that roughly every 8 months or so, if you were to take the slope, there has been a doubling in the number of model parameters for leading AI systems. Let's take a look here. This is GPT-3. This is the precursor to ChatGPT. And that thing has 175 billion model parameters in a transformer network. Now there's already larger systems than this. But an interesting thing is just like how much energy and time does it take to just train that kind of a system? I looked it up for GPT-3, it cost about 190,000 kilowatt hours to train GPT-3. That is equivalent to like booting up 20 humans up to their adulthood stage, which is roughly maybe 20 years old, I would say. So whereas humans are much more capable intellectually than GPT-3, you see a big discrepancy in how biology learns and how machines learn, many orders of magnitude, which shows us that like there exists a way, which we just haven't figured out yet, that you could make learning much more efficient. That is GPT-3. I recently looked up what GPT-4. So if you have paid the subscription for OpenAI, you might have played around with, I certainly have, you might have been playing around with GPT-4. GPT-4 was much more compute intensive to train than GPT-3. GPT-3 cost, as far as I could tell, over $1 million to train in energy. GPT-4 cost over $100 million to train. Okay, which is interesting also. This is getting to the economy of what a company can sort of muster in terms of financial resources. So now actually there's a pivoting a bit in the AI community to develop more efficient models because they can't play the scaling game anymore. That certainly makes a lot of sense, but nonetheless, there will be a push to building bigger and bigger systems. By the way, GPT-4 isn't even the biggest system. Like if you look at Megatron or so, those are bigger still. But if you want to continue this trend, and people will want to, there's a huge to do that. Like you have a new carbon dioxide, if you want to think about it that way, contributor, or perhaps you could develop new hardware. And I think this there. At the same time, we can also, if we look at the physics, and this is what I'll go through next, if we look at the physics, there's a big discrepancy also between what we know to be possible in inference, in energy of inference and training, and from the physics perspective, and what technologically is done today, many orders of magnitude. So we don't know where this will head, but this is, physics perspective, there's a huge gap, many orders of magnitude between what's possible, what's done today, and what's possible in theory. So let's take a look in particular at one of the leading systems for AI inference and training. Inference is really a bigger part in this paper, but I invite you to take a look, if you want to look into the training question, at subsequent papers by this group from the Google AI team. So this here is a sort of the most efficient architecture for doing these kinds of matrix multiplications. This is called a systolic array architecture that's optimized for general matrix multiplication. So again, it's a matter of multiplying vectors that we saw. Let's encode the vectors in one, let's say all the x vectors into one input matrix A, and all the weight matrices, the weight vectors into input matrix B. You can kind of like reshuffle it as you like, but this kind of systolic array, what it does is it sends the data in and computes at the point where these streams intersect the product between the two numbers and adds that to a local register. And in doing that over and over again, it does multiple in your system do per unit time. And how much energy do you pay per Mac? Those are the questions that are interesting for Boolean logic-based hardware. And we will refer to those, although when you look at physics, in physics computing doesn't care about max per se. I'll get to that in a moment. But this is sort of the most efficient system. And despite all the optimizations, incidentally, you can like run your code on, you can run PyTorch or whatever your favorite code is on the cloud on these kinds of TPUs. But despite all these optimizations, chips today are still dominated by data movement costs and not the raw processing power of the multiplier. And because of the tapering out of Moore's law, there's really limited gains for data movement. And so it's interesting to look at new hardware architectures. So let me, really point out two key limiters for this tensor processing unit. One is power. The more power the system burns, the greater of a problem you have with heat dissipation. And two, so you can't go as fast as maybe an individual transistor would allow you for computation. And two is the interconnects, feeding the data into this machine and data movement. So here is I want to go through in this talk and give sort of the main lessons that I've learned over the last 7 or so years and really studying and diving into this problem of AI hardware. You can see already from this slide one unnecessary but energy intensive part in computation. And that is that if we consider this input matrix here as the model parameters, and you consider a data center that is performing lots of, let's say, inference using on image processing, let's say, then all of these computers are reusing the same numbers. They're using the same model parameters, which have to be recalled from memory. So it's sort of it's like a redundant, really needless task that all these machines should get from their memory the same parameters and feed that into machine. Why don't you centralize that? You do one data access, and then you distribute those model parameters to all machines in a data center. You have 1,000 machines, million machines, all doing the same inference task. Okay, so this is a question of, in electronics it's difficult. You can't easily move in electronics data for long distances to all of the processors that want it. But if you use optics, you can have one machine that we call the weight server that serves up weights from memory and then just distributes those weight parameters, model parameters, to the processors in that data center. And so in that way, you've actually covered, you can delegate one of the biggest bottlenecks, because there's typically more model parameters that have the energy of having to retrieve the model parameters costs you about a picojoule per bit from model parameters to get stuff from DRAM. You can delegate that and basically amortize it out if you scale. Okay, and that's lesson number one. You should try to use data fan out for free when possible. Okay, this is where optics is good. Electronics difficult, you pay for it. Optics is good, you can fan out data. And the second thing is in physics computing, which I'll tell you in two ways. Number one here's one way of doing in physics computing. Suppose that we put the model parameters and we encode them into these so-called Mach-Zehnder interferometers, which are basically these optical switches that are tiled here in a cascaded way so that an input that is distributed over, in this case, 26 input channels encoded on optical fields, the amplitude of the input channels, that input, as it passes through this programmed mesh of Mach-Zehnder interferometers, is transformed to an output. This mesh can be represented as a unitary matrix acting on n inputs and n outputs. It's an n by n matrix. And the outcome is, if this is denoted as x, the outcome is x, u times x. There you go, in physics computing. And this is a particular type of thing called in-memory computing, actually. So the reason why this is useful for AI is that you can do the multiplication of a vector times a matrix simply by the physics of light propagation. So let's take a look. Now in the remainder, I'll actually get into the specific stuff that we're doing with these kinds of chips. Why is this? What specifically, what is the scaling advantage for doing things this way? Okay, if you used a conventional Boolean-based computer to multiply an n by n matrix by a 1 by n column vector, you might think about it. You have to, every element of that n by n matrix has to be multiplied with some number at least once. So the number of operations that you must perform for an n squared matrix by 1 by n vector is at least of order n squared. Okay, n squared operations. Now here, because the weights are stationary, that we assume them to be programmed and stationary, we must only encode the input, which is n operations, n, for example, digital to analog conversions, and then decode the output. Both of these operations are order n. So you have an order n effort in optics to compute the product of a matrix times a vector. Order n squared effort to do that by conventional methods. Okay, that's pretty interesting. There's somehow this physics here allows you to have a fundamental difference in the effort needed to perform a certain computation. I would say a certain map, whatever a computation is. Let's take a look at another example. Oh, by the way, this kind of chip led to two startups out of MIT that are now taking on the big boys in making machine learning accelerators. Not necessarily by this method, but by using in-physics computing and an efficient information fan-out. But let me give you another example for a fundamental scaling advantage for in-physics computing versus Boolean logic computing. Suppose that you have two fields, optical fields, X1 and WJ1, incident on a homodyne receiver, which consists of a beam splitter followed by two photodetectors, and you're looking at the difference current of these two. This is standard. If you've done optical comms, this looks vanilla to you. Okay. Now the law for the way that you compute the photocurrent is you take the sum. You look at the field incident on the detector and take the absolute value squared. That's proportional to the photocurrent. You take the difference. You see here that you find that the physics of the homodyne receiver automatically performs multiplication. Pretty sweet. Okay, that's commonly used, termed as the interference term. There it is. The interference term is doing a mapping of two input vectors, x and y, or x and w, and it maps it. You can extract from that the product between the two. Now, if you accumulate the photocurrent, like on a capacitor, or a switch capacitor in some of our work, then you sum these multiplications into what ultimately is a dot product between two vectors, right? So you've performed an inner product between two vectors. Now suppose that here you can have two fields, two long trains that could have 1 million symbols per field incident on this homodyne receiver, followed by this switch capacitor that does the integration. Your receiver doesn't do anything. It's just passive, sitting there, accumulating light, like in a photovoltaic. And only after all those, after that waveform has entered it, does it have to sample. So this is a very important point that people often miss for these kinds of devices. The sampling is when you pay energy on a photodetector when you sample its value. Just the charge accumulated on it, you don't pay for it. It comes from the light. So here we can evaluate the inner product between two vectors, regardless of how long they are, with an effort of 1. Again, a fundamental difference compared to conventional computing, where to find the inner product between two n-sized vectors, you would expend of order n operations. Here it's of order 1 operation, one that you pay for. Okay, that's basically the same idea as before, and you see again a different scaling. Now here in this paper, so I've thought of this back in 2016 or so, and then sort of played around with the idea, and luckily our team was joined then by Dr. Ryan Hammerly, with whom we actually did the detailed, he's a theorist with whom we did the detailed analysis of the implications of this kind of a compute. And this was published back here in 2019. And it assumed, okay, like what if we used that method to do machine learning? Basically, it's the same thing as on the previous slide. It's just more, it looks more complicated because you have to do it sort of, you have to do more fan-out. You combine actually the fan-out method and this in-physics computing. But the thing that I want to show you here is the energy per Mach equivalent. So in other words, if you were to use a conventional Boolean-based logic computer to perform a machine learning operation with this number of neurons per layer, this is the amount of energy that caps how much that Boolean computer could expend per multiply accumulate. And you see that at scale, the energy would have to, for a conventional computer to keep up with what the optical machine can do, it would have to, and by the way, here you see this, the benefit of going to larger scale. This is what we said, the order one compute versus order n steps for conventional computers. For a conventional computer to keep up with what physics says is possible with in-physics computing, it would have to break the laws of thermodynamics. This here is plotting the Landauer limit. This is looking at what is the minimum energy requirement to do Boolean logic-based computing for a, in this case, for a all-to-all layer connected with like 1,000 neurons. Okay, it's 1 million products. And that's the Landauer limit. We're below that. Okay, it's not saying that we're breaking Landauer limit. It's what we're saying is that an optical machine could compute at an energy efficiency that would, if you were to try to match it with a conventional computer, break the laws of thermodynamics. Okay, a strong reason to build these machines and test it out. And so that's what I want to tell you in the remainder here is actually using these principles to devise new computing machines, particular for AI, but also later touch on quantum control. But the second key point here is in-physics computing allows a fundamental scaling advantage in the effort to perform a map or a computation. Okay, now at this point though, we should check ourselves, right? I'm advocating that, hey, we should use analog machines for computing. And you say, wait a second, I've seen this movie before, right? Babbage machine and so on. And indeed, really out of that, really from when we started, we've been studying this problem carefully, the problem of error accumulation. In fact, in our very first paper, we were limited in the inference accuracy of our machine by errors. Okay, so this has been very interesting to us because we don't want to repeat these things. Although this is arguably the first practically useful computer, because actually somebody paid for it. The Navy paid for some of these machines. This is, from MIT by these fellows. And actually, incidentally, this is also an interesting paper. If you have a moment, you should take a look at it. This is the continuous intergraph by these gentlemen, and this was somewhat of an empirical time also for evaluating against compute problems. Just like the NISQ era today, a lot of parallels. And you see already in the opening abstract that errors of the machine have been reduced to an average of 1% for common uses. You see, they were using this kind of a machine against practically interesting problems and just saw, does it work or not, right? And so that's, I think, in many respects, what we're doing now with quantum computers, okay? But nonetheless, we need to solve this. We need to understand if these machines that we're proposing to build can in fact scale. Do errors accumulate in a way that we can't undo them? And the interesting thing about optics is that it's fundamentally different compared to these mechanical machines. And the fundamental difference is that errors in optical machines are coherent. A phase error can be canceled downstream. So if your machine is a little bit off in certain property, like there's a phase shift applied somewhere, in the beginning, you can undo that phase shift later on. You can't correct it perfectly. You can cancel it. And this is not possible with a mechanical machine, unless you can do coherent phonon stuff, which is very difficult. Okay, and so what we've shown actually in a series of papers, and I think in the interest of time, I just have to run through them here a little bit fast, is basically by studying the error properties of these kinds of machines and testing out different error cancellation, is that over a series of papers, which I give you here, we've come to this realization that at scale, when you have sufficiently deep optical meshes, for example, then you can become asymptotically fault tolerant. the bigger your system is, the more fault tolerant it becomes. Why? Because you have more degrees of freedom with which to cancel errors along the way. And that's a fundamental difference then compared to mechanical errors of the past. And so that's key point number 3. Coherent error cancellation is possible in these online optical systems. By the way, what limits it? There is a limit. You can't actually do it infinitely. The limit is the oscillator, the optical oscillator. But fortunately, laser oscillators are extremely good, extremely phase stable. All right, now I want to show you, in the last minutes I have here, what do I have? About 5 minutes or so? Then I want to show you how we put into systems. Build promise systems, I deliver systems. And so the first one I want to talk about is this single chip photonic deep neural network architecture, where we also investigated a new form of training. It's actually also different, but they're open questions, so you should try out new stuff. So let me show you here. This is a chip that was in the making for us for like 6 years. Hard to wire bond and so on. Incidentally, in talking to our NSF, remind them that we need more we make these amazing systems in the laboratories. They got to go out and do useful stuff. Yeah, packaging is very important. Following parts. Here's an input laser oscillator distributed into 6 paths. This is a rather small chip at this point still. With principle. This is the information to and then the waiting step, we must do some sort of nonlinear transformation, right? The neurons take in values and they have to transform it, ReLU or something like this. If you don't do that, then actually all these units combine it and realize as one unitary. Okay, you have to have the nonlinearity work to take sample the value electrically and then perform the nonlinearity external to the chip and then feed it back in, which gave like a huge bottleneck speed limit to how fast this kind of a machine could operate. In this work, we solved that problem. And the way we do it is by introducing a machine that called a nonlinear optical function unit. And this is what I want to focus on in particular, this programmable nonlinear optical function unit, or NOFU, as we like to call it. This thing here, what it is you take the input field and split off part of the input field, okay, that's coming into this neuron, using a Mach Zehnder, so it's programmable, into a photodiode, which then drives a modulator, in this case a ring modulator, and that ring modulator modulates the transmission of the remaining field here. So what you have is a process by which the transmitted field is modulated by the photocurrent here, which is the absolute value squared of the electric field. Okay? So if you're familiar with nonlinear optics, this you would call a Kerr nonlinearity. Because in a Kerr nonlinearity, the nonlinearity is proportional to the this is a programmable Kerr nonlinearity. When chip is that it doesn't have a component you would traditionally see in a kind of a receiver, which is there's no amplifier. Normally, when you have a photodiode, you must follow it with an amplifier, transimpedance amplifier or so. Why? Because you have to drive some current down some transmission line or whatever. You need to have some way of charging up the capacitance of this long wire. But it turns out, if you keep your wire short, then you need no amplifier. And that means that your energy consumption plummets dramatically because normally your detector is dominated in its energy consumption by the amplifier, not the light. It's the amplifier. So we this device not only super fast, because we no longer have the speed limit of the amplifier, but also very efficient. And so here's this nonlinear optical function unit in some detail. You have the Mach-Zehnder coupler here, and the photodiode here. The photodiode is a germanium photodiode that drives a ring resonator here that then, as I showed a moment ago, modulates the transmitted field. We use a ring modulator because it's a more efficient way of modulating light. And you see here the transmission of that ring modulator as a function of the input power. Okay? And when you look at the dynamics, it actually has some rich dynamics that you can program in by that first Mach-Zehnder interferometer. And in that way, you can program the nonlinearity. So sometimes, like people in AI have very loose, it doesn't matter. Like it's true, nonlinearities are universal by and large, but there is, in practical terms, there is an advantage based on the kind of map that you want to do.
Can you say something about how much voltage it takes to drive this chip?
Yeah, so the modulator operates at a swing of some fraction of a volt, like 0.3 volts. So when we look at the energy per swing of the modulator, okay, which for us is one operation. Every clock cycle, the modulator is a new level, okay, based on what comes in. And the energy consumption to set the modulator to a new level is, in our case, 10 femtojoule. That is a very low, this is 10 femtojoule per up. This is, to my knowledge, the lowest energy consumption modulator demonstrated. You might have seen previous claims of like 1 femtojoule per a bit or so. But those are extrapolating what it would be if you didn't have the supply line connected to it. But in this case, we don't have to extrapolate because there ain't no supply line, nothing. It's just that's what it is. So that's the big difference, that this actually reaches that level. And you can go about a factor of 100 or so lower in energy consumption. This is really just this is the beginning of what's possible. So this is an extremely low energy per operation, but we 100 times lower in energy. Okay, so to make a full chip that takes input with no time delay. You feed data in, data comes out, like the question comes in, the answer comes out in real time. Not quite, there's a speed of flight for light delay between the two. It's very small latency. But then we had a problem of how do we do this thing actually, this machine. And initially did what most people do in sort of analog hardware is they use a computer to train a model and then try to embed it in the hardware. That's a way to do it, and that's how we did it in the past as well. But for us, there was a new opportunity here because we have no latency in the output of this neural net. The paradigm, the conventional methods of backpropagation are not necessary because you get the inference immediately. So you can compute, you can train the system in new ways. And so we just tried various things, and here's one method that is described in the paper that just takes the output on the output with some detail that's in the paper. I think I don't have enough time to run into it, but there's a new way that you can compute this kind of a machine. Okay, we found that it's substantially better to train on the machine itself rather than simulate the machine in silicon and then transfer it. And that brings up an interesting question. I asked my students, like, I point this out, like, does this mean, because every machine is a little bit different, and when you train it, it sort of like corrects its own errors, actually, when it trains it, okay? You don't have to do tomography on it. It just like trains its own errors. And so every machine is a little bit different. They have a little bit fabrication differences. And so I thought this was kind of a beautiful thing, that all these machines are individual somehow. And you would have to train them like you train a biological, like a child. Do you have to train your robots as individual sort of like, do you have to like individually train your robot? Or can you transfer the information of one robot that was trained onto another analog robot? And initially I thought that this would be very difficult, but it turns out in this paper here, we found that if you architect the system right, that you can have an analog system that you train, and you take a copy, a close copy, but not identical, because no physical system is identical to another. And you can transfer the neural net that you've trained on one machine onto the other, despite their inherent differences. And we call this transferable learning on analog hardware. Yeah?
Are you still interfacing with some kind of memory? Or like, how does these... sorry. Are you still interfacing with some kind of memory, like off-chip, or how do you actually, because these weights have to iterate.
That's right. Yeah. So the model parameters in our case here are set using an SPI, using digital to analog converters. Those are applied external. But there are ways, and we have shown some and others have, to set the weights in a non-volatile way. One example is phase change material. Another that I think that we're doing is electronic flash, eFlash memory that's non-volatile.
But is that like interfacing with memory bottlenecking?
No, because it's stationary. Okay. Exactly. So our SPI interfaces can be arbitrarily slow. We fix them. Yeah, that's a great question though. Yeah, exactly. So take a look if you want more. Talk to me after. It's actually very interesting to me that one can transfer the thing. And so that points to the, I think, utility of in situ learning and training. Because even if you train on one analog machine and you don't know all the stuff, the intricacies that are coming out, you can transfer that onto another. And that actually has, in my view, also an interesting implication for training quantum computers. Do I have to do gate tomography? Do I have to develop error models for every gate in a quantum computer, which is very, basically impossible, very at scale? Or can you train on one and then transfer that onto others? I don't know yet, but so far we've analyzed it for that specific machine. Now, let me show you that's one system. Let me show you a second system quickly. And to this end, I want to just ask how much time I have now. Hey, Google, what's the weather like in Cambridge? Oh, come on. This latency, right? It's crazy latency. It's still thinking. Why? Because it's delegating that query to the cloud. So these edge devices delegate to the cloud. It's not smart enough. It doesn't have the processor to do the machine learning inference locally. Okay, but I told you that if we stream the model parameters to the cloud, to the edge devices, like in a data center, but perhaps actually to a network, then edge devices locally can perform inference, right? With not needing to actually retrieve the model parameters, which is one of the biggest bottlenecks, because you can have it streamed to them. So here we actually do this weight server, in this case I call it a smart transceiver, that sends model parameters to edge devices on a fiber network in the metropolitan area here of Boston. And we could actually do inference by receiving the weight parameters encoded in optical fields by this InPhysics computing. And I don't have enough time. This paper appeared here a couple of months ago. So for detail, take a look there or chat with me afterwards. Let me just give you the main point. So we used, in this case, we encoded data on the transceiver at 2.4 terabits per second, deployed over 86 kilometers of fiber in the metropolitan area using this fiber network that we also use in collaborators for quantum networks. And the edge device, we were able to show experimentally, could compute with just milliwatt of power at terahertz rates. So if you look at like a leading sort of node NVIDIA machine, it's about a watt per teraops per second. Here, it's about a milliwatt per teraops per second. And that's because it doesn't have to do all these things, retrieve memory and so on. And we tested it, although this is early days, okay, I don't want to overstate what's done here. We're just testing it on really toy models, okay, so really more work has to be done. This was done on MNIST, but at least in MNIST, which is like the simplest sort of image recognition thing you could do, we have equal performance compared to conventional computers. And in fact, if you look at the energy per equivalent multiply accumulate, in the optical field alone, we found that it can reach the same inference accuracy as a conventional computer with of the order of 1 photon per mode, per optical envelope. You would say, oh, wait, you can't do that. The signal to noise is awful for a single photon, right? It's true. But we're not looking at single pulses. We're looking at a train of pulses. And there, your signal to noise can be large enough, and that's why this is possible. Okay. Similar work here, we made use of the diversity of modes. Free space has a lot of optical wires that it allows, right? And so here we used a spatial light modulator to try out another aspect of this machine learning method that enabled us to perform over short bursts, 20 femtosecond long bursts, by just light passing through a series of spatial light modulators and other components. We could perform matrix multiplication at an equivalent of 20,000 multiply accumulates per pulse, 20 femtosecond long, which would, by that argument, lead you well into the exaflops. Now, it's not quite comparable. I put in a question mark here because exaflops demands, if you look at an exaflop computer, it's supposed to be double precision and so forth. But nonetheless, you can see that like these kinds of machines have a massive throughput. And really, the question is, how fast can you feed it? So to answer that, we've been developing, motivated by the optical quantum control questions, but also by these AI questions more recently, a series of high-speed spatial light modulator technologies that are based on this visible spectrum silicon nitride piezoelectric platform, based on, with our collaborators at CSUM, thin film lithium niobate, and here with our collaborators at Air Force Research Lab and at SUNY Polytechnic, silicon modulation. This device, for example, I just want to give you this at the very end here. I'll skip over this. There's actually another, this is also an interesting result, looking at another aspect. This paper here, in a separate work, we were able to do multiplication by injection locking to a laser. That turns out also does very efficient energy, low energy compute. But I want to just focus one last second here on this kind of a chip that you see here. We fabricated in a 300 millimeter wafer fabrication process using CMOS fab. This here is a spatial light modulator where every pixel can be modulated at nanoseconds. And that opens up the opportunity that you can actually really program optical fields completely. You have full degree of freedom control of the optical fields. And we showed that in principle in this paper that appeared a couple of months ago. But this is a quantum seminar, so can you control the quantum optical state of these optical multimodal fields? And for that, we can't do that yet, but perhaps we will be able to if we couple to these silicon, that modulator consists of a photonic crystal cavity array out of silicon, and if we can couple that device to these artificial atoms, then we would have cavities whose reflection is controlled by internal spins. There you go. So now you can connect it to quantum mechanics. And this is what we're headed towards. So we've just put where we were able to couple atomic defects in silicon embedded in these microcavities. I think we should be able to control the reflection of a single cavity with single spins. And that makes it possible to program not only the modes, but actually the quantum mechanical excitations of the modes in a way that's engineerable. Opportunities. For example, if you that operates like a deep neural network, but it processes information, it could do things that no neural network can do today. Like, for example, distinguish not between cats and dogs, but between the full basis set of Bell's. Okay, and so we show this in this kind of a machine. You can train a quantum mechanical machine to just like, even if you don't know the algorithm, to train it to do something, actually, to actually discover its own error correction algorithm, like one-way quantum repeater. And so now, last thing I wanted to mention, like along the way, you know, as you sort of take on hard challenges, I think you find opportunities where see that a technology should be spun out and or addresses some other need. And I've been fortunate to work with people, students from my group, but also collaborators here at MIT and Harvard, to participate in that kind of activity. And so when, for example, a team like my students here, Darius and Nick, go out and start a company like Light Matter, the one request is that if they're successful, they bring back something home, like these large-scale programmable meshes here. Okay, so because we can't build it in the university, if these devices have an industrial application commercially, then you can really, you know, put your ideas into practice. And so with that, I come to the final point here. Key points: use data to find out if possible. In physics computing can be fundamentally more powerful. Coherent error cancellation. Reach what we think is an asymptotic error correction in analog. And in situ training is a powerful way that could help solve some of these bottlenecks in training, the unknowns that we know they exist between biological systems that learn and machines that learn. Okay, and then I think there's a lot of really interesting connections between analog processing in the classical domain and the quantum domain. There's really no boundary, in my view. So with that, I should point out folks who've made that possible, and thanks for your attention. Happy to take any more questions.
Wanted to actually make a quick, brief comment. And, you know, this is a phenomenal example of the fact that science is circular, in the sense that, you know, when I was a young scientist, when I was your age, you know, the entire industry was interested in doing optical computing, and it didn't make any sense because we didn't understand neural networks, we didn't have modulators, and we didn't know how to do integrated photonics. And now the technology has caught up enough so that the actual science, I think, is being rediscovered.
Yeah, I like to joke it's called research for a reason. You have to research, got to research what you were up to back then. But on a serious note, I totally agree. And I think the thing that distinguishes mistakes from the past from just the time not being right is if you think through it like from a first principle. Here, if you're guided by the physics, it tells you like you can, you know, so far there's no evidence that we're wrong about these many orders of magnitude. So the physics says there's a big gap there, and that makes it worth pursuing. And just, you know, the time wasn't right before, but I totally agree. Great point.
Thanks for the very interesting talk. I saw your archive paper about the nonlinear optical function units some months ago. I read it. And I spent a long time staring at the figures about the different transfer functions that you're able to attain. And I think this might be a product of my own limitations, but I stared at those for a long time and was not able to conceptually understand how you could get these transfer functions that have multiple turns in them, just based on the intuitive thoughts about a ring resonator and the resonance shifting and this sort of thing. So I wonder if maybe even just for one of those curves, you could go through it and intuitively explain to me how you're able to get that particular transfer function as a function of applied power.
Yeah, let's see. We could do that. Let me give you so like we have SPICE models actually that I think if we haven't put them on, we've actually redone. So basically simulations that match the devices. But what happens here is that there exists there's a nonlinearity that is responsible for these kinks. And that nonlinearity is due to the diode behavior, because there's a diode in there, of the modulator. And so you have to solve the problem of a forward bias across the modulator under carrier injection. And so if you increase the input power, you can you have a nonlinear relationship. You have a nonlinear relationship between the photocurrent generated by the detector and the applied and the injection current. Because of the IV curve nonlinearity in the diode, the injection current
Diode of the modulator, the PIN
modulator,
not
exactly.
not the diode of the photodiode.
No, it's the modulator. Yeah. So there's a nonlinear, just the nonlinear behavior, threshold behavior of the PIN junction surrounding the modulator, and the actually it turns out even the optical response is nonlinear with the free carrier concentration, right? But there's a nonlinear behavior between the applied optical power and the free carrier-induced phase modulation. Okay, that's complication number one. Complication number two is that the response of the ring modulator in its transmission with the applied bias is also nonlinear because it's a ring. It has a Lorentzian line shape. So by the combination of these two, you get these funky, you can like bias one against the other, and you can get these different bias curves. And it depends on where you place the laser, the input laser with respect to the resonance of the ring in the off state of the device. So yeah, it's happy to talk about it more. We have the full SPICE models. It's
I think that what you said about the modulator might clarify it, because I thought that it was simple enough that as you're increasing the power, there's a linear increase in the photodiode current, and then that there's sort of a linear shift of the resonance.
Yeah.
But that's clearly
That's
not the case.
Yeah,
and
it's not
I
the
think
case,
that
exactly.
explains
And it
the
also
complexity.
depends on the bias voltage, it turns out, where that nonlinear shift happens.
The bias of the photodiode.
The bias of the photodiode, yeah, exactly. Yeah, this bias voltage here.
Thank you. Thank you.
I don't want to keep us from our pizza, but there's a lot of things that springs up to mind. And one of the things that Bill just mentioned that I noticed as well is, and I'd read an article about similar things in Wired magazine recently about analog computing coming back. When I was a lad, that was a thing. And they were, I assume you're familiar with the classic analog computing where
There's many areas actually, even for
capacitors and things together.
Yeah, and I mean for satellite imagery, analyzing satellite imagery, like actually radar signals, very difficult signal processing problem that uses analog.
Just out of curiosity, how many folks here actually know what an analog computer is? Have you guys learned about that sort of thing at any point? A little bit, yeah. It's very interesting and probably worth looking into because it's very analogous to what's happening here, but this is doing it on the circuit level. But the thing I was wondering about is much more system-y, is you guys are creating things that are starting to get back toward, we've gone off into the digital realm and are coming back toward the way actual brains work, synapses and neurons talking to each other and all that sort of thing. And you guys are enabling, this chat GTP 5, 6, 7, 8, whatever. Does it ever come up, or do you ever think about where the endpoint is, or if there is an endpoint, or need we be concerned about what that endpoint might be? I mean, you folks are the only folks I've ever heard of that are actually at that cutting edge. And, you hear about folks talking about it, Elon Musk and whoever, but is that something that you guys ever...
So first, I wanted to say that analog. Just even when you look at analog computers, I think the nomenclature is not actually particularly apt nowadays, because analog computer, it means, as you pointed out, it's computing by analogy. I think that machine learning is signal processing, and we are, more broadly speaking, I would say we're doing mixed signal processing in a way that can be vastly more powerful than conventional methods. A brain is also mixed signal processing. What are the implications of maybe future machines making use of these accelerators? I don't know, but I think some data points. If you project that line outward of the largest neural networks, if you just project it outward, you would see that before the end of the decade, machines will have more model parameters than there exist model parameters in a human brain.
That would imply.
And actually, in the human brain, many of the model parameters are not used for intelligence. They're, maybe, as far as we know, there are many other things that they're doing, and there's overhead and encoding and so forth. So I don't know. No one knows, right? I think the progress will continue, and I think it's important that one has a grip on the technology. So I think that it's sort of a duty that one must do this. One must investigate this, just so that we are that the free world knows how things are developing and masters this technology. That will happen. I also think that there's many open questions. We don't know. There's discoveries to be made, and it will just tell us more about how biology works. There's a lot of basic science that actually still has to happen and will happen. So, and also, I guess the potential for good things to happen with AI is vast. Is probably as big as it is for bad things to happen, I guess.
All right.
Great, thank you. Okay, so I do have a coffee cup for you.
Okay.
These are actually legal.
I need more
coffee cups
caffeine.
now.
Yes.
These are legal cups now.
All right.
I went through the trademark office finally to get the logo approved.
Okay.
And we will
Wonderful.
have T-shirts at the last lecture. So if you want to send students over for
Oh,
T-shirts,
fantastic.
tell them
Awesome.
they're more than welcome. So
Thank you,
let's
thank
thank
you.
Professor
Awesome. Yeah, thanks for doing
England again. And I believe there is pizza outside.